Hey folks, so as promised, this is a video showing the proof of this theorem, which says the following. So if V1 to Vr are eigenvectors corresponding to distinct eigenvalues lambda1 to lambda r, so all the eigenvalues are different, then the set V1 to Vr is linearly independent. Now, this is a really, really nice theorem. The proof I'm going to give, actually I'm going to do for just the case of two vectors. Now, this extends sort of nicely to, any set of R vectors, but I think just seeing the case of two vectors really gives you the sense of what's happening. And sometimes that's more important than sort of all the formalities. Okay, so we're going to consider just a set of two vectors, V1, V2. And we're going to study whether or not this is linearly independent or linearly dependent. Okay, so how do I study dependence, independence? Well, let's assume that I have a linear combination, right? So C1 times the vector V1 plus C2 times the vector V2 is the zero vector. Right, so suppose I have a linear combination of my two vectors v1, v2 that equal the zero vector. So just as a reminder, right, my goal, if I want to show that this set is linearly independent, is to show that C1 is 0 and C2 is 0, right? That only the trivial solution exists. Okay, if there were a non-trivial solution, this would be linearly dependent. Okay, so that's my goal. So how am I going to show that C1 and C2 are both 0? Well, with nothing else to really do here, I have to somehow leverage the fact that V1 and V2 are eigenvectors. So what does that mean? It means if I apply, let's assume they're eigenvectors associated to a matrix A. So if I apply A to either of these vectors, there's a way of simplifying that expression, right? A times V1 should just be lambda1 V1, right? So, with nothing else to do, let's just apply the matrix A to both sides of our equation. Just to see what happens. Okay, so on the left, I get C1 and then A times V1. And notice I'm applying linearity here, right, to split up this expression and to pull out the constants. But that's fine. And on the right-hand side, I have A times the zero vector. Okay, so I applied A to the left of both sides, right? And as I said, right, I can simplify this. And actually, I will sort of cheat on the iPad and just duplicate this. Okay, because, right, I can simplify this pretty easily. Okay, on the left-hand side, see A times V1, right? A times V1, as I said before, because V1 is an eigenvector, I can simplify that to just lambda1 V1, where lambda1 is the associated eigenvalue. Similarly, A times V2 should just be lambda2 times V2. And on the right-hand side, well, A times the zero vector is just the zero vector. Okay. So what did this gain me? Well, you might say, well, this didn't gain us very much at all, right? This is still a similar looking equation. Well, in fact, that's sort of the point. This is similar, and similar to what? Well, let me sort of quickly star my first equation I started out with, and then I'll sort of double star the equation I ended up with. And you'll say, well, these are really similar looking, right? In fact, what I can try to do is almost like think about this as a system of equations and try to solve them simultaneously in a way. So what if, for example, I multiply equation star by lambda1? Okay, just by this constant all the way across. What do I get? Well, I'm going to get, again, let me just sort of do a copy paste. So I'm going to get everywhere. I didn't give myself too much room here. So I didn't actually save myself time. So I get a lambda1, and then I don't want to forget my coefficients that were there. Okay. Okay, so I just multiplied star by lambda 1 everywhere. I sort of put the lambda 1s in between the C1s and the C2s, right, and the V's. Okay, fine. But yeah, so I multiplied by lambda 1. And of course, on the right-hand side, the 0 doesn't care, right? Now, this equation I ended up with, what if I took the equation double star and the equation I just ended up with and subtracted those from each other? Okay, so if I subtract these, what I end up with is, well, these first terms will cancel, right? C1, lambda 1, V1 are identical. These cancel. And what I'm left with is something that looks like this. So I have C2 times lambda 2 minus lambda 1 V2 equals, and then 0 minus 0 is still 0. Okay. So now, what can I say about this equation? Well, I can say a couple of things. This is really nice. V2, because I know it's an eigenvector, is not the 0 vector, right? That's part of the definition of being an eigenvector, is that we aren't allowed to take the 0 vector. The expression lambda 2 minus lambda 1. Now, remember, my assumption was that all of the eigenvalues are all distinct numbers, which means lambda 2 minus lambda 1 can't be 0 either, right? Because these are different numbers, right? So this is also not the 0 number. But what does that mean about C2? Well, if I have a non-zero vector and then lambda 2 minus lambda 1 is non-zero, but this whole expression on the left-hand side equals the 0 vector, well, it must be the case that C2 is the 0 vector, or 0 scalar, right? C2 has to be 0 for this equation to be true. That's the punchline. So C2 equals 0. Now, if I do the exact same argument that I did above, but instead replace multiplying by lambda 1 by multiplying by lambda 2, I'll get a very similar looking equation, but for the V1 vector, right? So let me not go through the entire process, but if we repeat with lambda 2 instead, right, of multiplying by lambda 1, you know, dot, 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 we repeat some steps, what we're going to get is the equation C1 times lambda 1 minus lambda 2 times V1 equals 0. And so by the same logic, we will deduce that C1 equals 0. But hey, that's exactly what we were hoping to show, wasn't it? Right? Because C1 and C2 were the weights of this linear combination, and we showed that they had to have both been 0 for this equation to have been true, we conclude that this set V1, V2 is linearly independent, right? Only the trivial solution existed. So we are done. Thus, V1, V2 is linearly independent. And we're done. So I think this is a really nice proof. It's really interesting to see how it works. If you have questions, of course, please let me know. The nice challenge for you to think about is how might this argument extend when I don't want to think about just 2 vectors, but if I have 3, 4, 5, and so on, can you think of ways to extend this argument or maybe modify this argument to work in those cases? If you get stuck, of course, we can talk about it, but your book also has a nice proof of this. Okay, great.